is from the technology to the use case. I want to share some work this morning. Well, morning for me. Um, that we did about the National Park Service units in the United States, with the idea of looking at their light pollution profiles as a guiding principle for management. And I want to add that this was, despite me putting together the presentation and presenting here today, this was all work that was done and predominantly led by undergraduates. Harrison, Shan, and Ben were undergraduates when I was at the University of Southern California, and did this as part of undergraduate research and demonstrating use of the data. I'm now at UCLA, University of California, Los Angeles. So of course, the National Park Service in the United States has a night sky team and has been building a considerable amount of both programming and science around the nighttime portion of parks. Series of posters produced by Tyler Nordgren talking about half the park is after dark. And so I was thinking about this and wondering about the way in which one would go about knitting together programs and perhaps educational materials across different parks, management strategies to achieve the goal of night sky protection, and to address all the many impacts of light at night, the ecological, the cultural, the aesthetic, and astronomical impacts. And so I was looking at the units by which the National Park Service manages its um, territory. And these are, I've cobbled together a quick map here. The Northeast, the National Capital, which if you aren't unfamiliar with the U.S. Park Service, they run most of what you would think of as being city parks in Washington, D.C., the site of recent events. The Southeast region, the National Trails, which is sort of an overarching set of territories that extend across many different regions. The Midwest, the Intermountain, so that's the big parks in the Intermountain West, Yellowstone, for example. Pacific West, which also includes Hawaii, and then Alaska. And these are the units by which the Park Service organizes its property management. And so the underlying question was really, is there another way that categorize these units that emphasizes similarities in their nocturnal environment? And how could this and nighttime remote sensing aid in development of light pollution mitigation approaches? It's a bit of a blue sky kind of question. They didn't come to us and say, hey, we'd like this question answered. This was an idea of wanting to look at these data and figure out what those similarities were, whether the geography makes sense, or whether there are ways to see links between parks that share common challenges that maybe could be addressed in common ways. And so this is the workflow for the project, which is basically consists of using the VIIRS day-night band as processed by Elvidge's group, and projecting it to an equal area projection. Then getting the National Park Service boundaries and creating buffer zones around them, because the question from a light pollution management perspective is not only what light is within the parks, but what about the areas surrounding it. And on the theory that nearby lights are potentially more damaging than faraway lights, we built a series of buffers around each of these units. Now there's over 400 of them, and you might say, I don't remember there being 400 national parks in the United States, and there aren't. They're all different units that are managed by the National Park Service that are in addition to the national parks themselves. So these would be national historical sites, historic birthplaces, trails, national monuments. So there's quite a bit of territory that doesn't necessarily reach the everyday awareness is being managed by the National Park Service that in fact is. And so around each of these 400 plus units, we created a 1 kilometer, 10 kilometer, and 100 kilometer buffer. And I know that impacts on the night sky exceed 100 kilometers, but we felt this was sort of a reasonable thing to get a picture about the neighborhood in a hierarchical way around each of these units to be able to compare and contrast them. We then overlay these in ArcMap, and actually early on we did this, and then we switched to a approach using QGIS and batch processing, and calculated the upward radiance in each of those areas, and then used Ward's method hierarchical clustering to create a series of clusters where the parks shared the maximum similarity within all these buffers and over all months. So we actually did this on a monthly basis over, and this I'm reporting here, I think we have two 48 months of data in this particular analysis here. The other side benefit of doing this is that then we have now a time series of upward radiance within each National Park Service unit and within buffers around it. So we can start to track and give insights about individual parks in terms of what's happening with this particular data set. And with all of its benefits and with all of its limitations as well, that I'm sure others have discussed here today. Uh, and as I look at this seems pretty simple. Um, it took quite a bit of time. There's quite a bit of data management here, and also a bit of heartbreak and anguish over getting small, complex units to extract the data from the raster. So small polygons in either, especially as we were working in an ArcMap, we would get a lot of failures just on implementing this workflow, and had to figure out what was going on, why it was we were getting those errors. And it had a lot to do with these small, complex park units that either were smaller than a pixel, so we had to give them a buffer, or um, other had complex geometries that just failed, to be quite honest. So we finally got around. We tossed some of the very, very small parks in Washington, D.C. for this reason, but ultimately got a data set of 48 months of data. And this sort of was the first test to figure out, well, you might think that these things correlate with each other. And the fact is that they do pretty highly. Those are the numbers going across. These are correlations between the light from within each of these parks. That's mean 0. That's with no buffer. Mean 1's 1 kilometer, 10 is 10 kilometers, and 100 is 100 kilometers. And I recognize that people are going to be upset that we've averaged it, the upward radiance, and already being by area, but didn't see another way to do this. And the interesting thing is that there is a high correlation between upward radiance within a park and a kilometer around it, pretty high, but it is not that high a correlation once you get out to 100 kilometers, which means, of course, as you might imagine, that parks are in very different contexts across the country, and this could be a reasonable means by which to investigate them. So here is so getting to results, here is the upward radiance, mean upward radiance within each of those units that are the current management units for the National Park Service. The one in the middle that has the largest numbers, that's NC, that's National Capital. The Northeast has quite a bit more, that's NE, Midwest. IM is the Intermountain region, AK is Alaska, and PW, Pacific West, and SE, Southeast. And at the end of the day, maybe the regional variations are better as a way there are quite a bit of similarities between them, and they're probably doing all right, but won't go down this route. We then created our own set of regions of parks and described each individual park within a series of classes that I'll get into in a second. We called them near bright, remote, standard, suburban, urban, and light saturated. And there is a slight improvement here, and I'll have to present this to the Park Service and see if they find the usefulness out of it. But it does give us a way to kind of think about the context in which these protected areas, or in some instances, the national parks are very much protected areas. Others are very urban. Grant's Tomb, for example, is basically an urban park, as is many of the national capital situations. So we clustered those out and then describe them. So our idea of a near bright park, these are parks that are have very little upward radiance within the park itself, but are very bright at 10 and 100 kilometers. And the example I'm showing you here is the Santa Monica Mountains National Recreation Area, which is in Los Angeles. I'm actually sort of sitting right about there. Um, and the interesting thing is the park or the recreation area itself, which is a combination of federally owned land, state-owned land, privately owned land, and includes even some includes residential neighborhoods within it. But within that, it's got a reasonable area of low upward radiance, but it is next to an incredibly bright city, and so we see that as being similar. And there are other parks and units that are classified this way. For example, the Indiana Dunes National Park, which is near Chicago, is a very similar thing. The park itself doesn't have a huge amount of light or very little light within the park itself, but it is near an incredibly bright location. So these are the near brights. Remote, this is sort of most of what we would think of as your typical national parks, the ones that you would have the most recognition as being part of the national park system. This is Zion and Yosemite and Yellowstone, Sequoia, Petrified Forest, Olympic. And they have very little upward radiance within the park and low upward radiance within 10. And usually as you get out to 100, you get regression to the mean in some, but these are the ones that have the most, I would say, astrotourism and are the best skies within the national park system. And now we have a list of those that all sort of meet this criteria, and we can cross-reference that with the monitoring that's done on the ground. Standard, and of course we can compare it with the World Atlas of Artificial Night Sky Brightness, which is another way to go about this assessment. Standard, these are low light within the park, but sort of average within the 10 and 100 kilometers. So things like the National Military Park in Arkansas, Channel Islands National Park in California, which has low light. It's on the islands off the coast here, but at 10 and 100 kilometers is quite bright because, again, it's dealing with Southern California lights within its sphere of influence. And I should mention the reason that I thought that this could have additional utility outside of simply taking the World Atlas and doing those calculations is the location of the brightness. Whether if you had something that is within a particular region, it's sort of out from the park, it suggests different kinds of approaches from a mitigation. If there were incredibly bright things in the 1 kilometer outside a dark park, then emphasis would need to focus there. Similarly, with 10 kilometers, with 100 kilometers, then we're talking about regional policies. And so this was a way to sort of get at some of those influences and what the challenges are from a policy perspective of parks trying to manage and protect dark skies, of where to put emphasis going from the park to a kilometer to maybe they're right outside the park. There are vendors or park associated tourism facilities that could be approached or at the 10-kilometer range versus needing and pursuing regional policies at the 100-kilometer range. Hence this approach. Suburban parks, moderate levels of park within it, moderate light within the buffers, and this is one of the eye-opening things about doing this is that despite the view of our national parks, there are a lot of units that are in these suburban and then, of course, also urban context where it's bright within the park, bright surrounding it. The Lincoln Memorial in DC follows in this sort of moderate within and surrounding. And then our last category were these light saturated ones that were just actually some of the brightest things on the landscape, mostly in Washington, D.C. Our White House is is lit up far beyond reason, I might say. So those are the categories. And I sorted out the actual national parks here by the two categories that they fall into, which are the remote and standard. And you can see the standard, the 100-kilometer buffer is over here on the right, and it is the ones that have the higher, the blue bars. A lot more light at the 100-kilometer brings you from being a remote park into the standard category. So, for example, up here we have Channel Islands National Park, which is very little upward radiance from within the park itself, but quite a bit from within the 100-kilometer buffer. So its challenge, of course, is keeping these numbers down within a kilometer and 10 kilometers, but has this regional challenge of just where it is. Hawaii features here with the lowest light at all of these. Dry Tortuga is, of course, an island off of Florida, so it has quite a bit of an advantage. On the mainland, Big Bend National Park has the least light within it at the buffers and within 100 kilometers. Death Valley, also very well known. Canyonlands, Grand Canyon, Great Basin, Redwood, all familiar dark sky locations. And then we pop out these ones that are getting closer to major light sources. So Joshua Tree pops out here, and Kings Canyon, Carlsbad Caverns. And so what we're suggesting here is that these parks have some things in common that perhaps can be shared and have shared management approaches as you go across it. And then some of our brightest one, Wolf Trap Farm Park, is pretty bright, and also is a pretty large visitor serving facility on it. So this isn't entirely surprising. So there's a whole list here, and then if we were to go through the whole 430, we can now rank these by within park light, surrounding, and these buffers. So just to talk a little bit about some examples, the time series that then come out of these, and I should, speaking of time, be looking at the time, make sure I'm not going over, is the Mediterranean network here. Again, this is Los Angeles. These are the Channel Islands National Park that I just mentioned. This is actually Cabrillo National Monument down in San Diego. And so we have these time series to look at, and can extract more of these data and add it to. You can look and see the interesting thing here is just how much higher the average radiance is a kilometer out than even 100 or 1 kilometer. Of course, at 100 you get regression to the mean, but at 10 kilometers there's something really fascinating going on there on a seasonal basis. And that happens to be a tomato greenhouse that's in an agricultural zone just west of the park that comes on during the winter time when they're doing tomatoes. And we have complemented this with a transective ground-based hemispherical imagery. This is an area outside of the recreation area, but about a kilometer and a half, 2 kilometers from that the tomato greenhouse that causes the sky to glow yellow. The one on the left is a 30-second exposure when that greenhouse is not operational. That's about 20 millilux scalar illuminance as measured with a sky quality camera. And then on the right, there's more cloud cover, so that's influencing it, but that's a 15-second exposure and 80 millilux. So there's about 4 times increase in the ground-based illumination with that greenhouse on versus the greenhouse off. And so that suggests to, and I've shared actually this with that park, that there may be some outreach needed and some policy needed relative to the operation of greenhouses in facility in vicinity of these facilities of the national recreation there. This is Channel Islands National Park, so this is off the coast. Again, we describe this as a standard park because there's so much light in the 100-kilometer, but there's also here quite a bit of variation at the 10-kilometer area that I wasn't picking up in the long term of the veers. A little bit of an upward trend as well in the within park 1 kilometer and 100. And so we had a look at that, and this is a work that another undergrad did, 𝗖cie když I just want to show it. This happens to do with the fact that there's a commercial squid fishery that uses light-induced attraction of the squid to the surface in order to get them. Uh, and and we did another analysis using some data provided by 𝗖cie když and his group, looking at this park. So the islands here are Santa Cruz, Santa Rosa, Anacapa, and these polygons are actually areas of marine protected areas where we're not supposed to be fishing. And these are the density of lights, point detections and their brightness using a point detection algorithm out of 𝗖ć's lab. And looking at that, and so these are squid fishing locations. Every one of these spots here is a squid fishing location, and it's a seasonal fishery, and so that explains the lights changing over the course of the year. And we also saw a dramatic increase over the time period. If we look at the yearly change, this should, yeah, so you can see we're looking up here within this circle. This is Southern California coast, and you can see the movement of those squid boats over the 4 seasons. So this is going from spring, summer, winter, spring, fall, winter. And so they're moving around there. And also we looked at it over time, and they're increasing. So it sort of really draws out what's going on this park by looking at the buffer around it and the temporal changes in the veers that then, through this separate analysis, correlate with, and we can confirm is really being driven by this light-induced squid fishery. And so this is what that looks like. This is a picture that Ben Benet, one of my co-authors, took getting the data out on Santa Cruz Island to compare with the satellite data. That's a squid boat. That's one boat illuminating the shore there, and leads me to sort of question about this is maybe that each park is unhappy in its own way. To paraphrase Tolstoy, there are all these interesting issues that are going on, and looking at the data this way perhaps give us a way in to connect up the remote sensing to on-the-ground phenomena to management challenges, and in this instance, the management and impacts from the squid fishery, but other things in other parks, but also to share similarities, educational materials that might work for the Santa Monica Mountains National Recreation Area near Bright could also be applied in other near Bright parks where you've got the ability to get away from some lights and some astronomical observation, but also the incredible challenges of being near a light polluted landscape. So I wanted to share this just sort of as a use case and a demonstration of the value of free and open data, to be quite frank. The ability to access these and set them up in a workflow and get a lot of them is only possible because these are free data, and also that it starts to build the next generations of students interested in this topic, and going on to further work on light pollution topics as they proceed as well. So with that, I will end. And